Hello. I'm Kyotaro Tokoro. Today, I'd like to talk about our multimodality-aware metric for probabilistic human motion prediction. Here is the outline of my presentation. First, I'll talk about HMP task. Human motion prediction or HMP is a task to predict future motions from observed past motion. Motion data are represented by the x, y, and z coordinates of key points. Human motion prediction has an important property: multiple future motions can follow from a single past motion. For example, given a past motion of sitting, a person may continue sitting, stand up, or even lie down. In other words, the distribution of future motions is multimodal. Now, I explain a multimodal distribution of motion space. As mentioned earlier, the three different future motions can be considered as forming separate peaks in this distribution. A distribution with multiple such peaks is called a multimodal distribution. Here, we define a mode as a set of motions corresponding to one peak. In this example, the motions can be categorized into three different modes. Because multiple future motions are possible, recent human motion prediction methods aim to capture multimodality by predicting multiple future motions from a single past motion. Next, I will explain two requirements for multimodality predictions. The first requirement is coverage of possible modes. A multimodal prediction should cover those multiple modes. A low coverage prediction like this left side biased toward a single mode. In this case, even if multiple predictions are generated, they all look very similar. However, even if a prediction covers multiple modes, spread out predictions like these don't satisfy the second requirement, validity. In this example, some predictions lie far away from the distribution. Such out-of-distribution predictions often correspond to physically implausible motions, such as motions with abnormally long limbs, or future motions that are inconsistent with the observed past. Therefore, validity of predicted motions is also a crucial requirement for capturing multimodality. As discussed so far, multimodality in prediction is characterized by two requirements: coverage and validity. In this work, I propose a metric to evaluate multimodality in predicted motions. Next, I'll talk about the existing metric on human motion prediction. In recent methods, probabilistic models have been proposed to generate multiple future motions from a single past motion. Next, I will explain existing evaluation metrics that are used to measure whether the predicted motions are sufficiently diverse. This metric is called APD. APD computes the average pairwise distance between all predicted motions. Intuitively, when the distances between predictions are large, APD assigns a high score, assuming that diverse motions are predicted. Conversely, when the predicted motions are close to each other, APD is a low score. Now, the key question is, can APD truly evaluate multimodality in prediction? First, let us consider the first requirement, coverage. APD only measures distances between predictions and does not explicitly consider prediction modes. Therefore, APD cannot evaluate whether all plausible modes are actually covered. For example, based on these distances alone, we cannot tell which prediction covers more mode. A more critical problem arises when we consider validity. APD does not evaluate validity by comparing predictions with ground truth motions. As a result, APD can assign high scores to predictions that are widely scattered but include abnormal or implausible motions. Therefore, APD cannot properly evaluate multimodality in prediction. Let's move on to the proposed metric for multimodality. APD does not consider prediction modes, and therefore fails to evaluate coverage. To address first issue, I perform mode detection and evaluate predictions based on the detected modes. Regarding validity, when multiple future motions are possible, evaluating validity requires multiple plausible ground truth motions for a single past motion. Therefore, I use multiple pseudo-ground truths. I will now explain these two components in detail. First, I introduce mode detection. To evaluate coverage, we need to detect modes based on differences in motion. Therefore, I formulate mode detection as a clustering problem in the motion space. We cluster a large-scale motion dataset. However, since motion data is inherently high-dimensional, it is hard to detect cluster boundaries. Therefore, we first apply dimensionality reduction to obtain a low-dimensional motion space. From this point on, for simplicity, I will explain the method using this two-dimensional projection, where the height dimension is omitted. Next, we perform clustering on these points. Since clustering groups together similar motions, we treat each resulting cluster as one motion mode. Next, I will explain multiple pseudo-GTs. To evaluate validity, predictions need to be compared with GT motions. However, in existing datasets, for a given past motion, only one future motion is observed as GT future motion. To evaluate multiple plausible future motions, we require multiple GTs. Therefore, we construct pseudo-ground truths in a data-driven manner. Specifically, we compare the given past motion with past motions from other sequences. If the past motions are similar, we regard the corresponding future motion as a plausible future, and treat it as a pseudo-ground truth. Conversely, if the past motions are dissimilar, we assume that the transition to that future motion is unlikely, and do not include it as a pseudo-GT. In this way, we can define multiple future ground truths for a single past motion. Next, I explain how our proposed metric is computed using mode detection and multiple pseudo-GTs. First, given a past motion, the motion prediction model predicts multiple predictions. Next, using the method described earlier, we construct pseudo-GTs from the past motion. These predictions and pseudo-GTs are passed through dimensionality reduction and projected into the motion space, where clustering has already been performed. By mapping them into this clustered motion space, we can identify the mode of each prediction and each pseudo-ground truth. In this figure, each mode is represented by a black boundary. We highlight modes that contain pseudo-GTs in light blue. These modes represent the modes that should be predicted. Finally, based on the results of this mode assignment, we quantify validity and coverage. First, let me explain validity. Validity measures how many predictions fall into plausible modes. Specifically, it is computed as the fraction of predictions that belong to pseudo-GT modes. Next, let me explain coverage. Coverage measures how many pseudo-GT modes are actually covered by predictions. It is defined as the fraction of pseudo-GT modes that contain at least one prediction. Finally, we compute our proposed metric, MMCM, as the harmonic mean of validity and coverage. By taking the harmonic mean, the score becomes high only when both validity and coverage are high. Let's move on to our experimental results. We use Human 3.6M, which is a large-scale motion capture dataset. We evaluate MMCM against these HMP methods. This table shows the evaluation results of each method. Here, APD is the conventional metric that simply measures the average distance between predictions. As we can see, MMCM and APD rank the methods differently. To investigate which metric better evaluates multimodality, we analyze the predictions of DELO, which achieves a high APD score but a low score under our proposed metric. This is one example of a predicted motion. As we can see, the arm becomes abnormally long. Since abnormal joint lengths can be detected by measuring bone lengths, by removing such abnormal motions, we obtain a set of predictions with higher validity. We then compute APD and MMCM for both sets. As shown in the table, APD assigns a higher score to the predictions that include abnormal motions. In contrast, MMCM assigns a higher score to the predictions after removing abnormal motions. These results indicate that our metric correctly evaluates validity. Next, we examine whether MMCM can correctly evaluate coverage. This figure shows overlaid visualizations of multiple predictions predicted from the same past motion by two different methods. If we focus on the final pose, compared to the left method, the right method includes a wider range of plausible motions. For example, motions that fall backward or bend forward. This suggests, qualitatively, that the right method covers more diverse futures while remaining within a plausible motion range. Next, to verify whether this qualitative observation is consistent with MMCM, we compute MMCM. In both cases, the right method achieves a higher score than the left method, which is consistent with our qualitative observation of coverage. The number of pseudo-GT modes that are successfully covered is 2 for the left method and 4 for the right method. To further analyze the mode detection results, we extract one representative prediction from each covered pseudo-GT mode. The representative predictions are shown in the bottom row. As we can see, motions such as falling backward and bending forward are identified as distinct modes. This indicates that our mode detection correctly distinguishes different types of motions. Therefore, MMCM appropriately measures differences between modes. In other words, our metric can properly evaluate multimodality in prediction. Finally, I summarize my talk. Thank you.